Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
Good morning. Can everybody hear me? Yes. Good in the back? All right, good. Okay, so I'd like to thank Myron and Fred and the S&P organizers for all the work that they've put into this and for inviting me to talk to you this morning. And thank you all for coming, in spite of it being game day. I do appreciate all the seats being filled. All right, so as he said, I'm going to talk about the sun as a star. And since you're here early on a Saturday morning, maybe I don't have to motivate why this is an interesting thing to talk about, but I'm going to go ahead and I'm going to start by motivating the problem. Why do we care about the sun? And then I'll start the first half of the talk. I'm going to focus mostly on the sun itself. I'm going to talk about phenomena that we observe and the things that cause them. And along the way, I'm going to be pointing out things that are going to come in parallel in the second half of the talk when I talk about young suns. All right, so as far as the motivation, why do we care about the sun? I think this video just about says it all, assuming that the video is going to play. All right, so what you're seeing here is a solar storm. You're seeing a trifecta of things happening in this video. In the very center, there's some flares going on in the middle. I don't know if you can see those. Let me replay the video. So in the center, there are flares going on, and at the same time, you see coronal mass ejections. And all that little snow and fuzz on the detector is high-energy radiation. It's particles, energized particles hitting the detector. So our nearest neighbor is very often manifesting this violent activity that's aimed in our direction. And that's a pretty darn good reason to care about what it's doing, because this activity can cause nice things like aurora, but it can also cause pretty bad things. It can cause radiation that's dangerous to our astronauts who are up there in orbit. And exactly. And it can cause power outages. It can damage our power grid. It can damage our satellites. So we need to understand what the sun is doing. And I'm going to totally date myself with this next joke, but it would be really nice if the sun had a Facebook page. And then we could just check, and it could warn us, hey guys, I'm going to send a CME your way, look out. Earth and everybody else can prepare. But unfortunately, we don't have this kind of an update system. The sun just isn't with social networking. So what we have to do is study the sun and figure out what drives these phenomena and figure out a way to predict them. Okay, so as far as the sun in context of all the stars around it, it's actually a fairly average star. What I've shown here in this figure is a histogram. It's called the salpeter initial mass function. And what it's telling us is that if you look at regions where stars are born, and you look at them when they're fairly young so that you can catch the highest mass stars that have just formed and haven't lived out their very short life cycles, you tend to observe a function of this form. And you see very few very, very high mass stars, and you see a whole lot of low mass stars. And we are here. We're kind of mediocre. We're in the lower mass range. There are a whole lot of stars out there that are a lot like the sun. Okay, so on the interior of the sun, this is just a very rough schematic of what the different regions are inside of the sun. And these boundaries are not nearly as rigid as this would imply. At the center, you have hydrogen fusion, which is going on at temperatures of tens of millions of degrees. And then as you step out throughout the sun's atmosphere, the temperature starts to cool. And then at the surface, you have the temperature that I showed on the last slide. The effective temperature is defined as the temperature at the visible surface of the sun. And then you go higher into the atmosphere, and you have the chromosphere, a transition region, and then the corona. And the transition region is a very interesting place because some very strange physics happen in a very rapid, a very short distance. And so you see the temperature goes from the surface temperature of 5,000, 6,000 Kelvin or so, and it just shoots up to 1,000,000 Kelvin. And the corona is very, very hot. And the density at the same time decreases by many, many orders of magnitude. So the corona itself is this very tenuous, very hot gas. And the reason that we know what the temperature of the corona is by looking at different species that are ionized in the corona. And something that's really, really interesting to me is that iron 2 million degree indicator. that iron is actually ionized 17 times. The corona is so hot, it has just ripped off all these valence electrons, and you're seeing iron in this state in the corona. It's very hot. Now, if we look back at the surface of the sun, you see granulation. And these granules are a lot like just a boiling pot of water. This is a video of granulation at 60 minutes that's been compressed into a few minutes so that you can see all the different kinds of motion. Oops, I'm sorry. I'm going to play this video one more time. This is a lot like looking down on a pot of boiling water. And I don't advise actually doing that. It's probably not safe. These convective cells are hot plasma that's rising from the lower levels of the solar atmosphere and then sinking down again. And for scale, this is the size of the US. These structures tend to last about 20 minutes and then they disappear again. So while we're thinking about the sun, what we need to keep in mind is that it is a plasma, which will behave a lot like a fluid, but you also have additional physics to take into account because it is so hot. There are lots of charged particles flying around, and that means that it's going to interact with magnetic fields. And so you go into a regime of physics called Magnetohydrodynamics. And it's actually quite straightforward what MHD is, even though it sounds really complicated. You take your standard fluid hydrodynamics description, and you fold into it the Lorentz force. And when you do that, you end up getting a situation where if you have energy deposited in a certain place in the plasma, it does not travel kind of like an acoustic wave. It has a directional dependence because of the presence of the magnetic field. And that will become important later. But that's all that's special about MHD. So if you ever see this phrase, don't feel like it's lofty or very hard to understand. It's quite straightforward. Okay, so within the interior of the sun, you have magnetic fields being generated at the core. My slides are not advancing. Okay. And these bits of magnetic field are traveling from the interior of the sun up to the surface. And because you're talking about a charged plasma, these tubes are subject to stress and strain. And when I talk about a flux tube, I'm talking about a bundle of coherent magnetic flux. So it's a bunch of magnetic field that is coherent and holding together. And it is subject to several different modes of stress. And so what's happening as this tube rises to the surface, a little demonstration material. Let's imagine that this yarn is a flux tube in Michigan colors for today's game. As it's coming up to the surface, it's being moved around by the convective motions. There are small scale eddies, there's large scale motion. The tube itself is magnetic field, and it's filled with a plasma that has a density and properties of its own. So you have a density gradient from the inside of the tube to the outside, and that causes it to rise. It gives it buoyancy because the pressures are different inside and out. And on the way, it's getting buffeted around in the atmosphere, and it's getting these different modes of energy deposited into it. And what's effectively happening is the kinetic energy of the plasma is transferring into magnetic energy. So now this energy is stored in this field line, in this flux tube. So then, when it gets up to the surface, you actually observe this kink. This is the projection of this field emerging from the surface towards you. It has a funny little S shape, and what you're directly observing is this kink, this helicity that's stored in the magnetic flux tube. And these are called sigmoids because they look more like S's to me than the Greek letter sigma, but they're called sigmoids. And we can see that it has that structure, and you can make out in the right picture the individual structures that go into the entirety of the flux tube. You can actually see them because they're filled with plasma as they're emerging from the surface of the sun. Now sigmoids and this emergent flux stays together because it has a pressure density that's different from the outside. So the sigmoid itself, it has magnetic pressure that's battling the plasma pressure around it. And it's just enough to hold together, but the plasma pressure is still great enough that it's twisting this flux tube. So another form of emergent flux that you may be familiar with that is a case where the magnetic pressure dominates the plasma pressure is a sunspot. And so this is an illustration of an active region on the sun, and the Earth is shown to scale. So these are very, very large. And what's happened here is flux has emerged from the interior of the sun, and the magnetic pressure is actually so great it's stopped convection in that area. And so you get a local cool spot because no more hot material is allowed to come in there and replenish and make that area as bright as the surrounding areas. And so we observe sunspots over a course of a cycle, the course of the sun's magnetic cycle, which is 11 years or 22 years, depending on how you look at it. And what we see in the sunspots as they move across the sun is they form this butterfly diagram. And what's happening here is in the early stages of the sun's magnetic cycle, the flux is emerging at higher latitudes, and then later and later in the cycle, you're seeing it emerge at lower and lower latitudes. And this is a product of meridional flow, which is an organized large-scale flow inside the sun that goes from pole to equator. And it's driving these magnetic features down towards the equator. Now, one thing I really, really love about this diagram and just about solar physics in general is that this time axis starts in 1870. We've been observing sunspots for a very, very long time, and there's just a wealth of data on these. In fact, in a historical context, sunspots have been observed as early as 800 BC by Chinese astronomers. And they would often do their observations by looking at the sun when it was low on the horizon, and so they had enough cloud depth between them to not hurt their eyes, or they would do it when it was foggy out. Please, please do not do this at home. Use proper viewing equipment. And the interpretation of these things, you can sort of tell when this PowerPoint, I'll put it on my personal homepage, it has a link to the archive that has these ancient data. These are actual transcriptions of the Chinese astronomers' records. In the quote on the left, you can see sort of what they're talking about. There are frequently shadows at the center of the sun. Okay, those are sunspots. And then a later one, they're talking about the darkness recently visible in the sun. It's a bad omen. And they also talk about black vapor, which, as it turns out, is another manifestation of this emergent flux coming out. The black vapor that they're talking about is what we call a filament. Okay. And on the sun, when we see these filaments, they are tubes of magnetic field that have made it from the surface. They've emerged, they've survived and remained coherent, or they've been buffeted around as they've made their way buoyantly up through the solar atmosphere. And when we see them in our line of sight, they're called filaments. And when the sun rotates and they go off to the side of the point of view, they're called prominences. It's the same thing, just a different name. Okay, so these are all representations of magnetic phenomena that actually maintain coherence. But as we know from physics, we know that systems tend to the lowest energy state. So you put all of this kinetic energy from the convection and from this buoyant motion, you put it into the field lines, and they're all twisted, and there's so much energy stored in the field. It suddenly spontaneously reconnects and releases all of that energy. And that's what you observe when you see a solar flare. It's a spontaneous reconnection of these fields. And the general picture of it, which we know from actual observations, there's a hot loop, and what happens is the magnetic energy is released at the top of the loop, and it goes up as well as down. And the energy that goes down because of MHD, because this is charged material, will follow the magnetic field down to the surface of the star. The energy hits the surface and it evaporates the material. It creates a little shock localized at the foot points of these loops. And you can see the shock. In the upper left-hand panel, that's an EUV, an extreme ultraviolet image of a flare. And then once that material has been excited, it fills the loop, and then the entire loop is illuminated in the soft X-rays. And that's what's shown in the cartoon on the right, and that's what's shown in the bottom left panel of this graphic. And then there are other forms of energy release. In the bottom right panel, the soft X-rays are shown with the hard X-rays, which are the higher energy X-rays. Soft means lower energy, hard means higher energy. And when we observe this at Earth, you might have seen it classified with a letter, like an X-class flare or an M-class flare. And this is what it means. GOES is the Geostationary Operational Environmental Satellite, and it records the full disk X-ray flux from the sun as a function of time. And that's what you're seeing in the figure. That's flux as a function of time. And what they've shown on the y-axis is what the energy scale is. And I've put a little key, a little legend on the left that tells you exactly what the orders of magnitude are that they're talking about. The letter corresponds to the order of magnitude, and the number out front is the multiplier of that order of magnitude. But the take-home point from this figure is that X-class flares are the most powerful ones that we see on the sun. And the next most powerful are M, and then C. Okay, I have a couple of videos of solar flares. You can see it happening in the ultraviolet just off the right side of the limb. This is a SOHO UV instrument. SOHO is the Solar and Heliospheric Observatory. I apologize, NASA has a lot of acronyms, and I don't always catch myself before I just say the acronym without actually naming the satellite. So the one on the right is the video from SDO, which is the brand new observatory that they just recently got first light from over the past summer. And this movie is just unbelievable to me. There's a C-class flare that's going on down lower in the atmosphere. That's that yellow brightening. And then the material that's being launched from right above it, that little dark lane, that's a filament just being erupted away from that site. Because like I said, when the reconnection occurs, the energy doesn't just go down into the foot points, it also goes up. So very often with flares, you'll see a filament eruption occurring at the same time. It's just blowing away everything that's above it. Okay, so another form of magnetic activity we observe on the sun are coronal mass ejections. And these are related to these large-scale magnetic structures I've been talking about. In this picture, you see a time progression of a coronal mass ejection. And the first time is in the upper left, the last time is in the upper right. You just go right across. And if you look at the graphic on the far right, there's a brightening right in the center of that. That is a filament, and it has erupted in association with this coronal mass ejection. And something that's really interesting about coronal mass ejections is that they actually remove so much plasma from the corona that it causes a net dimming of the sun's emission in the UV wavelengths. So these phenomena are very often related. And here I'm showing a video that includes what they call a solar storm, which includes the flare, the CME, and the particle event hitting the detector. So these phenomena are very often associated. It's not clear why. You have CMEs that occur without flares. You have flares that occur without CMEs. You have them that occur together sometimes. And I'll talk about my research in a little bit, but the best way to think of them is not necessarily as causally related to each other. They're both byproducts of this magnetic reconnection and the release of this energy in the field. So it makes sense if you have enough energy release, you're going to see both phenomena. Okay, finally, the final slide of the solar section, we also observe the solar wind. And this is a continuous stream of particles that is bombarding our magnetosphere and us. And it's very low. It has a very low mass loss rate, so we don't have to worry about it in the way that we would a large CME pointed at us or something like that. The image on the right is a Ulysses satellite recording of what the solar wind speed is. And so if you picture the sun's total magnetic field like a bar magnet, you have a bar magnet with iron filings around it. The large scale field of the sun is dipolar. And so you get very, very fast solar wind coming out at the poles. You get very slow wind at the equator because it has to work its way through that field, and the charged particles and the MHD, they're interacting, they can't get through. And then you get the faster wind at the other pole. Okay, so I'm going to take a moment and rewind. So we are here. We are at the very last panel on the bottom right. We have a solar system and us, the sun, and that's about it. If you look back in time, this is the canonical picture of how the sun formed. And we have come to understand this by looking at other stars. So we see all these complex phenomena now, but what do we see back then? The physics are much more complicated because we begin by collapsing a dense core, and then the dense core gravitationally attracts all of the material near it, and that continues to collapse and get warmer, and the pressure builds, and eventually you have a protostar. And it also has an accretion disk. And the accretion disk and the star have a really complex interplay that greatly affects the things that we observe on young stars that we would compare to what we observe on the sun. Okay, so this is a canonical way that astronomers understand stellar evolution. It's called the Hertzsprung-Russell diagram. It's a really great tool for visualizing how stars change over time. And what it does is it relates the effective temperature of the star, the temperature at the surface, to the luminosity of the star. And what you see on the figure are models of stellar evolution, and the dot dash lines are lines of constant age. They're called isochrones, iso being the same, chrone being age. And then all of the curved lines are mass tracks. So stars don't maintain the same mass throughout their lifetime, and they don't maintain the same temperature on the surface. So the magenta line represents the path of the sun in time. So back at the top, when it was a young star and it had a disk, it was very red. It was a little bit cooler than it is today, and it was much bigger. So this is about a 2-to-1 ratio then to now. So the sun starts out up at the top of that magenta line. It's a K star. It's very cool. It's very, very large, and it continues to contract. And so that contraction is directly reflected in the downward path of that curve. As it contracts, the luminosity goes down because it has less surface area to radiate over. So it gets fainter and fainter and fainter. And then that point where it curves, it goes from what's called the Hayashi track, which is named for the astrophysicist who first characterized it. It goes from the Hayashi track to the Henyi track. And at this point, it's got enough radiative energy at the core that that's starting to counteract the gravitational collapse. It's not quite fully hydrogen burning. The core isn't quite fully radiative yet, but it's on the way. And then once it's done, it gets to the point where we see it now. That last line of constant age is what's commonly referred to as the main sequence. This is when the radius is stable, the pressures are balanced between collapse and the radiative pressure, and you're on the main sequence, which is where the sun occupies most of its life. It spends most of its life on the main sequence. Okay, so let's rewind back to the young solar case. This is the Orion Nebula Cluster. You've probably seen this really spectacular image. And when we look at this, if you zoom in on certain locations, you see stars being born. You see stars embedded in these natal cores. They have envelopes and disks, and you can zoom in on them and see the great array of morphologies. In this bottom panel, the second plot over, you can actually see a disk inclined with respect to the star that's blocking out the light from the star. So, like I said earlier, when you have a disk around the star, you greatly complicate the physics of what's going on. And you have to start worrying about how the star and the disk are interacting with each other. And these are a couple of graphic renderings of what's going on during the accretion phase. And the drawings are meant to convey a couple of different things. So on the left, what's being emphasized is the fact that the magnetic field is interacting with the disk, because the disk is charged as well. It's partially ionized. And what you actually see in this figure is the magnetic field being bent by this interaction with the disk. And this is thought to actually slow stellar rotation, potentially. In the right figure, the emphasis is on the accretion process. The magnetic field itself reaches out from the star to the inner edge of the circumstellar disk, and it just funnels material from the disk onto the star. And in this particular case, you have a really interesting geometry where the rotation axis is perpendicular to the disk, but the magnetic field axis is slightly tilted. And so that adds all kinds of different degrees of complication. Okay. So we have measurements where we can calibrate the way that this takes place. And this is a really loaded plot, but we're going to walk through it and get through everything. All right, so what I've shown here is, as a function of age, how much mass is transferred. And what I mean is mass from the disk onto the star, and from the star out of the system altogether. And I've put a whole bunch of measurements on here. One thing to note is that the age on the x-axis is logarithmic, so it's artificially expanded the first 10 million years of the star's life so that you can actually see these points on the left. Otherwise, that's just a blip in the sun's history that barely even just happened in a snap. All right, so what the purple diamonds are showing at the very top is what the mass loss rate is for young stars. This is actually measured through their spectral lines. The orange dots are for the same stars, what their accretion rates are. So at this point in time, you're gaining more mass through accretion than you're losing through winds. The orange line, if you keep going ahead in time, and imagine that this is the sun progressing from the upper left to the lower right, the sun is that little pink point all the way over on the right today. It has a very low mass loss rate. Through the middle of its life, the way the sun loses mass through the wind is characterized by this orange triple dot dashed line. And what's happening there is the sun is still evolving. It's still contracting as it goes down that slope. And that little blip is that transition onto the Henry track where the radiative pressure begins to dominate. And then also on this plot, what I'm showing is the infrared excess fraction on the other y-axis. And what that's telling you is whether or not the star still has a disk. So when the star has a disk, you still get accretion. Those green points are in the same area as all the points of mass loss. And when the star loses a disk, you now have a situation kind of like the current day sun, where you just have a wind and you're losing mass that way. You're not gaining mass from the disk at the same time. All right, some other things I've shown on here just for sort of Earth-centric reference. Each of the geologic periods, as we understand them, is highlighted in a different bold bracket of color. And that point with the two white vertical lines represents the late heavy bombardment, which is when there was a catastrophic event where material from the outer solar system came into the inner solar system and bombarded the Earth and the moon. So this is important to keep in mind. It informs our view of how our solar system formed if we understand this history of the mass flow in the system between the disk and us, and then out. And then around this epoch where planet formation starts, we really need to understand what's going on so that we can understand how planets form and how they evolve. Okay, so to condense this figure into a few points, the things that can take from this is that, first of all, the accretion phase is very, very short. The initial phases are very, very rapid. They happen incredibly fast. Over time, all of these things are observed to decrease. The disks dissipate, accretion stops, the winds slow down, until you get to the solar case today, where the wind is actually very weak. So if we look at the sun, and we go back and remember our MHD picture, think about accretion material that's free falling in from the disk onto a young star. What might that do to the star? Well, we have sort of an idea from the sun. So there are currently a couple of satellites called Stereo A and B, and they stand for ahead and behind. And these two satellites were launched such that they could get simultaneous views of the sun from different angles. And that's to map the three-dimensional structure of these things that we're really used to seeing in two-dimensional projection. So this is the Stereo Ahead spacecraft, and it's observing a coronal mass ejection, and then what happens after the coronal mass ejection. So the magnetic energy release has gone upwards to drive the CME, and it's gone downwards, and it's driven a wave in the upper atmosphere of the sun. That is an MHD wave. In some sense, it's kind of like dropping a rock into a pond, and you're just watching the ripples go. But it's more complicated because the magnetic field is involved. But it looks exactly like that. If you look at the Stereo B spacecraft, where you're looking at this event progress face on, you see the exact same wave, and it's propagating almost circularly. So now in the context of the young star, if the accreting material is hitting the surface, what that can do is actually drive material into an enhanced wind. So this sort of speaks to the question of why did the young sun have a much stronger wind than the old sun does? It's quite likely it's accretion driven. So in this cartoon, you see material falling in along the magnetic field lines, hitting the surface, driving these MHD waves, and pushing material to open field lines where it can then escape from the star. Okay, so what I'm kind of touching on here is an area called the solar-stellar connection. And what we do is we take analogies between the sun and stars like it and use that to further our understanding in both separate fields. One of the first areas where this was actually done had to do with stellar flares. And we observe flares on stars. We observe them frequently, and they're very, very powerful, especially on the youngest stars. So what is shown here is a light curve from an X-ray observation of the Chandra-Orion Nebula Cluster, of the Orion Nebula Cluster by the Chandra spacecraft. And I showed the Orion Nebula Cluster a few slides back. And the light curve looks exactly like the solar case that I showed a few slides ago. Now, if you look at a video of this region, you see all these little twinkles. And this isn't twinkling like, in the sense of atmospheric turbulence as you would normally see it if you just went outside on a warm night. Every one of these little twinkles, these little bits of light, is a flare that's going on in one of these stars. They're very powerful, and they happen very often. Now, if you look at this a little bit more closely, and you compare it to the solar case, what kind of flare are we talking about? If you classify these young star flares, and TTS stands for T Tauri star, which is just the name of the first sun-like young star that was observed in this particular class. If you classify them like you would a solar flare in the same energy range, it's 100 to 10,000 times stronger. These are extremely, extremely energetic flares. Okay, so extending our solar-stellar analogy, what you can do on the sun is simultaneously observe, I'm going to skip ahead a slide because this one's a little bit more illustrative. You can simultaneously on the sun observe a spatially resolved structure, and you can observe the light curve. And you can watch how that system evolves in both methods. But on the stellar case, all we have is the X-ray flare. So what's been done is people have taken these spatially resolved solar flare data and related them to the X-ray decay curve. So you have a loop that has filled with soft X-ray plasma, and when that plasma cools, it cools via two mechanisms that can be pretty well characterized. It cools by radiating away energy, and also by conducting energy back down to the surface. And when you compare that process to the actual decay in the X-ray light emission, you can derive from the light curve alone what the size of the loop is that's containing the material that's emitting that light. And so this was done for the stellar case, and what they found was that on these young T Tauri stars, these loops are absolutely huge. So in the solar case, we see these little loops. They look huge to us, but they're less than a solar radius. But then in the stellar case, this is what the loops look like. And this is a small example. I didn't have enough pipe cleaners to actually make the 10 stellar radius one. Budgetary constraints are a hassle. So this seemed totally unreal when this result was first published. It seemed absolutely unbelievable. If we look back to past observations, though, there are other large-scale structures. That huge loop is effectively a prominence. That's what it is. It's an enormous loop that's suspended out beyond the corona of the star. So what has been observed in the past are cool structures. So what I've shown in the diagram on the right is a light curve that is taken as a series of time. And they've put in these helpful animations to show you that what they're observing is the star is rotating and there's some sort of suspended cloud of material. And as that passes between you and the star in the line of sight, it causes a little dimple in the light curve. And you can model that, and you can figure out roughly how big that structure is. And because it's co-rotating with the star, they knew the rotation period beforehand. They can figure out how far from the star it is, and roughly at what angle it might be projected. And so they found that these cool clouds that were absorbing light from the star were actually of order this size. They were tens of stellar radii. So these things kind of jive. All right, so if you take the solar analogy and you look at whether or not it's possible to get a really, really extended loop, there you run into a problem pretty fast. In the solar case, with a solar-like plasma that's scaled up to the physics of a slightly larger star, slightly cooler star, you actually can't get hot loops to be very tall. You have a lot of forces that are counteracting each other. You have magnetic tension that's keeping the loop in its shape. You have magnetic pressure that's trying to lift the loop. And then you have the difference in the plasma densities inside and outside the loop. And that leads to either positive buoyancy, where the loop rises, or negative buoyancy, where it falls. And when you balance all of these different forces, if you have a loop that has cool material in it, it's really easy to get it very, very extended, out beyond the atmosphere of the star. But a hot loop, not so much. However, remember what I said about the wind. The wind is much, much stronger in this young stellar case. So when you add the extra force of an outward wind, these loops can actually be stable. And so what I've shown on the right is the results of some of our modeling work. It's a little obtuse, but basically the point is just that the y-axis is the maximum height that you're able to get for a loop of a given temperature when you turn the knob on some other parameters. And we managed to get loops that could reach out to 6 stellar radii, which is consistent with the observations on young stars. All right, so in the solar case, we sort of see something like this. Now, it's really interesting to think about these large-scale structures and whether they can exist and whether they can be stable, but it's a lot more interesting to think about what happens if they're not stable. What happens when they explode and run away from the star and escape? So this movie just makes my jaw drop. There's the perfect storm, the solar storm, flare at the surface, CME that expands out away, and this filament just stays together. The size scale here, that little dot inside the red coronagraph, is Venus. Venus just got walloped by this solar storm, and it just kept going. Now take this and look at a T-Tauri star and scale up, look at a young sun, scale up the energies, scale up the frequencies, and then you have some young planets that are in a lot of trouble. So the ramifications of this, the increased activity level, the increased energies involved, they change the structure of the disk as it's even forming planets. It can cause shocks within the disk that start formation of grains, and that changes the way that heat travels throughout the disk. If you have a planet that has already started to form and it has a little tenuous, wispy atmosphere, you hit it with a really high energy event and you blow the atmosphere away. And then there go your little microbes that were forming at the surface. Another thing that it can do is, if you think about it from the perspective of a simple consideration of the torque. So let's say that I'm the star and I'm rotating, and I have an extended amount of material out here, and I'm rotating, and all of a sudden that material is lost. This is my lever arm, and it actually affects the way that I rotate when this material flies away. So we found that it can actually change how fast the star spins. Okay, and the way that we have characterized this, start talking about some of my own work. We took a distinctly astrophysical, astronomical approach to analyzing solar data. So solar physicists, I must say I'm rather envious of this. They have very, very huge, very rich data sets. They can simultaneously observe something in multiple wavelengths with high spatial resolution, high temporal resolution, and astronomers, especially if you're an X-ray astronomer, you're lucky if you get a photon. A photon is a detection. Okay. So it's like, all right, we have this rich database of flares on stars, which is what we can observe. we can't observe the CMEs. So what I did is I looked back at solar data and related the flares and CMEs on the sun. And so what you're seeing here on the left is a histogram that shows the distribution of CME masses from 11 years of data taken for the sun. And the solid distribution, the black one, is all of the CMEs, and the red one is just the CMEs that are associated with flares. And likewise, the same thing is shown for flare energies on the sun, the full distribution of flares, and then the flares that are associated with CMEs. And something we found that was really interesting when you're thinking about really, really high energy stellar flares is that on the high energy end of the solar flares, we found almost 100% of the time a flare and a CME happen at the same time. And this makes sense. If you go back to what I was saying about how reconnection occurs, when the magnetic energy is released, it releases energy both up and down. And if this single magnetic reconnection event is the driver of multiple different events via some partition of energy, you would expect that the properties of the two things would be related. And the more energy is involved, you would expect the more different phenomena to be observed. And indeed, this is what we found. So this is a plot of the CME mass versus the flare energy for flares and CMEs that were correlated to each other. So if they happen at about the same time and about the same place, I counted them as correlated. And the really interesting thing about this is that the relationship holds this log linear form over orders and orders of magnitude, which definitely hints to fundamental physics that are connecting these two processes. And so the next thing that we do is we look at the energies of flares on stars. Because we know what the energies of the flares are, we don't know what the CME masses are, but we want to characterize what this mass loss is from these enormous lever arms so we can see how it's affecting stellar rotation. So the range of energies that are observed on young stars is shown in this plot by those vertical triple dot dashed lines. So you can see these solar flares, like I said, they were 10 to 100,000 times weaker, and that's just evident in this huge chasm in the plot between what we see on stars and what we see on the sun. So to sort of check, before I boldly went ahead and folded the frequency distribution of flares on stars, which is shown in the inset figure, against this relationship for the sun, I took about the closest proxy that I could for the CME mass on the stars. And that is, when they were modeling those loops to figure out how tall they were, they had X-ray data. They were using the X-ray light curve decay to figure out how big the loop was. And so by taking the ratio of different species in emission in the X-ray data, you can get a density. So you have the loop volume and you have a density that gives you a mass. And these loops could be akin to these filaments that are erupted with the CMEs, like I showed you from the solar data. And I plotted those loop masses up there in red, and they scatter right around the extrapolated relationship, which is encouraging. So we went ahead and we calculated what the mass loss rate would be for these stars, given this frequency distribution of flares and this relationship of flare energy to CME mass. And what we found is that on young stars, the mass loss rate via coronal mass ejections would be about 1,000 times more than on today's sun, than today's solar wind mass loss rate. Now, does it affect stellar rotation is the next question. So what we did for this is we calculated several torques within the system. So when you have material, sorry, let me rephrase. When the star is collapsing, you have this canonical picture of angular momentum conservation, of the ice skater pulling in her arms and spinning faster and faster. And that's what the star is doing as it's collapsing. It should be spinning faster and faster, but that's not what we observe. So somewhere the angular momentum is not conserved in this process of collapse towards the main sequence. So we characterized what a bunch of the different torques would be. So if the star were just collapsing on its own, nothing were slowing it down, you would see what the black line is showing. And what this is spin up or spin down time scale as a function of age. And spin up or spin down means how much of a torque would you have to apply to either spin the star all the way up or slow it down to a stop. And at any point in this diagram, any age, the torque that is at the bottom, that means it has the shortest time scale of action, is going to be the dominant torque in the system. And so for the first early part of the star's life, it's this contraction that's spinning the star up. That's what's dominating everything. And then these red and these blue lines represent the torques that the CMEs are applying against the star, the different mass loss rates. And there are a couple of different parameters in here that have to do with whether or not the CMEs are happening continuously or they're spaced out as we actually observe. And so if they're happening continuously, you get the dashed lines, you get a more efficient mass loss. And then if they're not happening continuously, you get the dot dash lines. You have a much less effective torque against the star. And so what we found is that indeed within this time scale during which planets are forming and the disk is evolving, this mass loss rate via coronal mass ejections is actually could slow down the star. Okay, so what I've shown you over the course of this talk is that you can take solar physics and you can apply it to stars, and you can learn about how the stars evolve from young suns into the sun as we observe it today. I've shown you that you can turn around and take methods that astronomers usually use and apply it to the sun and learn something new about the sun. That mass to energy relationship is something that hadn't been done before. And when you look at these young stars in context of young suns and piece together their evolutionary history, we'll eventually be able to understand just how our solar system came to be. So, thank you for your attention. Finishing a little early.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.